Hi, and welcome to the Hydraulics Laboratory in the Faculty of Engineering, Computing and Mathematics at the University of Western Australia. Today we're going to look at a physical model of the Swan River in Western Australia. In environmental engineering, we use this model as a teaching tool, and it's often convenient to use a physical model in the laboratory of a very complex system like the Swan River. The reason for that is that in a laboratory model, it is easy to manipulate the model and to investigate certain sets of conditions. When we create a model like this, we try to make a scale model. So a model that has the same proportions as the real system, but is scaled down in every dimension. So the camera is looking north. There we have the CBD, the river flowing down to the ocean at Fremantle. The horizontal scale ratio of this model is 5,000 to 1. In real terms, the distance from Fremantle to Perth as the crow flies is approximately 20 kilometres, and we have condensed that to 4 metres in the laboratory. So horizontal length scales are reduced by a factor of approximately 5,000. We can't build a true scale model, however, because the vertical dimension of the model has to be artificially increased. The average depth of the Swan River is of the order of 5 metres. Reducing that by a factor of 5,000 will create a 1 millimetre deep model. And when we create a 1 millimetre deep model, the physics of the model starts to break down in that effects such as surface tension and viscosity start to become important when in the real river they are not. So we exaggerate the depth by a factor of approximately 50. So here we have the river, and here we have the ocean water, which we will now make salty so that its salinity matches that of real ocean water. And we'll also add some blue dye to it so that when it enters the model, we can quite clearly visualise it. What we're trying to do here is we are trying to make measurements in the model and use our understanding of fluid mechanics to infer the values of those parameters in the real Swan River. So for example, if we measure a certain current speed in the model at the East Fremantle Yacht Club, what does that mean for the actual current in the real Swan River at the East Fremantle Yacht Club? You have to understand fluid mechanics to know how to do that, but that's what we're going to work through today. So the first thing we're going to do is try to create real ocean water with real ocean salinity. So to do that, I have to add approximately 3 scoops of salt to the volume of water shown here, and I'll do that now. 2 scoops and 3 scoops. So by adding that amount of salt to the model, we're going to create water here that has a density that is 2% greater than that of fresh water. It's a very small change in density, but the fact that salt water is heavier than fresh water impacts the dynamics of the Swan River. So what we have to do is we have to mix the salt water fully through this volume so that it's nice and well mixed. We don't have any salt remaining undissolved on the bottom of this ocean reservoir. Okay, so I'll add a little bit of blue dye. And then mix that in. So what we do now is we just check that we've made water the same density as salt water using a hydrometer. We put that in the water, and where the gauge intersects the surface of the water, we can read off the density. And so looking at that, we have a density of roughly 1,020 kilograms per cubic metre, which is the density of real ocean water. So what we have now is we have ocean water that is separated from the fresh water of the Swan River, and this was very much the case in the 1890s, where there was a limestone sill separating the river from the ocean. At around that time, in order to create Fremantle Harbour, that sill was destroyed, and what that allowed the ocean water to do is then enter the Swan River. So that's what we're going to do now. We're going to open this gate, effectively destroying this limestone sill, and we're going to allow ocean water to enter the model. What we want to look for is the way that this heavy ocean water enters the model that currently contains the lighter fresh water. It enters as a nicely defined gravity current flowing along the bottom of the river. The system is minimising its potential energy by having the salty and heavier water flowing along the bottom. So we're going to open the gate now, but do look at the way the water enters the model as a gravity current along the bed. So now we open up the model and we can see the blue water flowing along nicely. We have salt water now entering the river and we have fresh water flowing out towards the ocean. And so what we'll see is that there is a very distinct boundary or interface between the heavy blue salt water and the lighter fresh water. So you can see the salt wedge now moving up into the ocean. It moves into the river. It moves quite rapidly. It sticks to the deeper parts because it is heavier. But what we're seeing now is the creation of a two-layer fluid within the model. We have the fresh water in the upper layers and the salt water in the lower layers. And there's not a lot of mixing between those two fluids. Now, in the Swan River, this is detrimental in a lot of cases to the quality of the water in the river, because we have this heavy water that is sitting over the sediment bed, we have this lighter water above it, and if they don't mix very rapidly, the bacterial processes in the sediment deplete the lower waters of oxygen. And because that oxygen in the lower waters is not being replenished through mixing, the oxygen levels in the lower waters gets very low, creating anoxic conditions, which is then detrimental to the large organisms in the river. So what we see now is the salt wedge moving up the river, still confining itself to the lower regions. And if you look through any of the observation windows, you can see that there's a very precisely defined, very thin interface between the light fluid and the heavy fluid. So what we're going to do now, once this salt wedge has entered the model, is to make the model more realistic. And one of the things that we can do is we can turn on the tides. So a lot of the flow in the Swan River is driven by the tides. We don't have particularly large tides in Perth. The maximum tidal range is roughly 1 metre, but it does have a dominant influence on the flow patterns within the Swan River. So to study the tides, we have a tidal generator out here in the ocean. When we turn this on, this will move up and down at a regular frequency that corresponds to a 24-hour tide. It turns out that in the laboratory, a roughly 3-minute period corresponds to 24 hours. So we have to understand our fluid mechanics to know how we go from the real values in the system of 24 hours down to a 3-minute tide in the laboratory. So now that the salt wedge has reached its equilibrium position, we're going to turn on the tides. And what we should pay attention to is the amount of mixing that the tides generate. How much mixing of heavy salt water do we get with the fresh water? Because up until now that has been largely absent. So we're going to turn on the tides. Okay. So now this box is rising and that's creating an ebb tide. So water is rushing out to fill the void underneath this box, and in the river that's creating the ebb tide. So if we look at the water now, we can see it rushing out towards the ocean. What's pronounced now with the tides is that the addition of kinetic energy from the tides is creating turbulence. So in regions of the river where the motion is fast and where we have rapid changes in geometry, such as around the Swan River Yacht Club and Blackwall Reach, we get a lot of turbulence. That turbulence mixes the blue heavy fluid with the clear lighter fluid. So we're now getting mixing of the salty and the fresh water that we didn't have before. So the impact of the tides is to create mixing between these two fluids in the river. So we can see along this region turbulent eddies that are creating that mixing. And that's a very important impact of the tides in the Swan River model. In some time, that tidal generator will reverse and start to move down, and that will create a flood tide which will drive water into the Swan River model and will drive the salt wedge up and into areas around the CBD. So now the tidal generator is moving down, it's creating a flood tide. We can see the water rushing into the Swan River. Turbulence is generated in these areas here, creating a lot of light blue brackish water, which is what we find in these regions, and it's pushing the salt wedge further and further up into the estuary. So the mixing generated by the tides is very important so that we don't have that density stratification in the river, which in turn creates problems with low oxygen levels, which in turn creates some of the fish kills that we observe in this river on a regular basis. What we want to do is measure velocities in the model and use that to make an inference about velocities in the real system. So what we can do is we can inject some dye into the model and see how high the velocities are in this area and see how we scale that up to the real system. So suppose we want to know the velocity of the East Fremantle Yacht Club. When the tide reverses, what I'll do is I'll inject some dye, I'll time how long it takes to move a known distance, and then use that to calculate the current velocity in the model. I take some red dye, and I inject the dye and start the watch. Now I've measured out this distance, and we know this distance is along the river 90 centimetres, and now the dye comes past. So the dye took 9 seconds to travel 90 centimetres. So the velocity in the model on the ebb tide is 10 centimetres a second at East Fremantle Yacht Club. So how do we calculate the actual velocity in the river? I said earlier that the scale of the model is 1 to 5,000. This is 5,000 times smaller than the actual river. But that doesn't mean that we multiply the velocity here by 5,000 to get the real value, because 10 centimetres a second multiplied by 5,000 is 500 metres a second, which is faster than the speed of sound. So the scaling of the velocity is very, very different to the geometric scaling. Now, when you learn a bit about fluid mechanics, you'll know that the Froude number is very important here. And when you understand the importance of the Froude number, you know that the ratio of the real velocity to the model velocity is not 5,000, but is in fact 10. So the real velocity here is 100 centimetres a second, or about 1 metre per second, which is a very realistic value. So we can go from measurements in the model to make inferences about flows in the real system. So what we can do now is we've turned on the tides, but what we haven't turned on are the freshwater inflows that come into the Swan River estuary. So we have the Avon River and the Canning River, which are a source of fresh water. And what we see is that in winter conditions, the fresh water coming in from those rivers actually makes the water around the city much fresher than it would be otherwise. So we turn those rivers on in the model. So now we have fresh water coming in from the Avon River, fresh water coming in from the Canning River, and we figure out the flow rates in the model again by understanding the importance of the Froude number, which tells us how to create our scaled model. One thing you notice is that the flow rates coming in from the rivers are very, very small. So the appropriate flow rates coming in from the Canning River is just a drip every second or two. So the impacts of the rivers are not profound, certainly with respect to the tides, but they do have some impact in keeping the water around the city and in the upper reaches of the river fresher than they would be otherwise. So we have a very, very slow flow rate coming out of our rivers in this particular point in time. And we know that the water, even around the city, can get brackish and salty, especially in summer, to the point where the river dolphins can move past the Narrows Bridge. So in summer, when there's no fresh water coming into the system, or very little, the water around the city is still comparatively salty. In this movie, you've seen how we can recreate the flow patterns in the Swan River through the use of a physical model in the laboratory. We hope that this movie leaves you with a better understanding of how freshwater and saltwater interact in an estuary, and also that it has helped highlight the beauty of fluid mechanics.